in seconds. Here's the temperature. These three curves represent the test with diesel oil, the pool fire test, so we see a very fast growing. And then we see a very sharp decrease when the water mist system is turned on. Temperatures are dropping below 40 degrees. These tests, these are the results of the solid fires. This one is the big one. And then when the water mist system is turned on, we see a drop of temperature, but then it slowly increases until a maximum of 700 degrees. The average temperature around the tank were about, let's say, 60% lower. Now this is the response of the tank. Again, we show the different test results here. Now the time is now until 1500 seconds, so it's a slightly different time scale. But again, you can see here the three results of the pool fire test. Temperatures rising very fast, but then when the system is turned on, they also are decaying. And then here we have the other two tests with solid fire, and this test is showing that when we do not start the sprinkler very fast, then there will be high temperatures of the tank wall. This sheet shows the average heat flux into the belly of the tank, into the water. And again, you see that with the pool fires we have the highest heat flux, and that is because the pool fire is situated lower, and then the flames are going under the tank, because we also have ventilation in the tunnel. And when we have a solid fire, then the flames are much higher, so they are not so much underneath the tank, but more on the upper part of the tank. So the principle of the assessment of the blast risk from the test results was to predict the actual stress in the reference tank and then in the shell of the tank due to the pressure built up in the reference tank. It was shown from a simulation study that the end caps of the tanks were not important in this respect. So the pressure built up is caused by heating up of LPG inside the tank, and the heating up of the LPG is calculated from the measured tank shell temperatures with a simple lump parameter model, and then the heat flux into the wet part of the test tank. They were just directly measured and just corrected for the difference in area. Then we have to predict the decline of the maximum allowable stress in the shell of the reference tank, because this will decline, the shell will weaken because of the heating up of the tank shell, and we can calculate the maximum allowable stress directly from the temperatures we measured on the shell of the test tank. So if we combine these things, if the actual stress exceeds the maximum allowable stress, then you cannot neglect the risk on a blast or the risk on a rupture of the tank. Here's some results then. Again, we see time and then the pressure in the calculated pressure in the tank, and the pressure built up in the last test here, where we delay the suppression, is of course going to be the highest. Now here's a combination of the test results. Here we see all these tests, and we see the decline of the allowable stress. And again, this red one is the one with the heavy goods vehicle with 720 pallets. And here, this is also the actual stress in the last test, and here we see some critical things happening. So, but for the other test, there's a difference big difference between the results. So the only critical situation will occur then in the last test, and you really delay the suppression. So it seems that I have some time to go into detail. As I said, the amount of heat going into the liquid was determined on the temperatures with a rather simple lump parameter model, and then the heat flux into the liquid from the belly was directly measured, and this was the biggest part of the absorption. I mean, maybe 80%. So there are some relations given between the absorbed heat and the temperature for different LPG fillings. They just depend from the thermodynamic properties. And then you can see that you can, from the temperature, then you can determine the pressure, build it, the vapor pressure in the tank. And then from this vapor pressure you can determine the membrane tension or the stresses in the tank shell. So this one is an important one. This has to be compared with what we can allow, and then again we have to determine the critical heating up time. We can make a distinction between low tension and high tension. So if you have a low tension, it's based on the low duration of steel with these kind of formulas. And when we have high tension, it's based on the ultimate tensile strength of steel, and this is the curve we used to determine that. Finally, some conclusions. I think the effectiveness of a watering system to prevent a BLEVE was successfully verified with a mock-up in a full-scale fire test, but I have to make a remark on that later. And only when the activation time was really purposely delayed, then there occurred after 400 seconds a risk of a blaze. But this is not a representative situation. In the other test, fire was extinguished or controlled quickly. So for a pool fire test it's extinguished, but for a solid fire it's not extinguished, it's only controlled. And you can see that quick detection and extinguishing of the fire is very important, particularly when you have a pool fire, because you have a very fast increase in the temperatures around the tank, but also increase in the wall temperature itself. So I would like to thank Sintap and BL Microchip Systems, and of course our Ministry of Public Works for funding this work. Thank you for your attention.